I'm going to be giving a presentation that'll be updating the results from the DART test that happened a couple years ago. But I have a few charts that I want to go and present ahead of that because I thought it would be appropriate to do so. The first chart here shows a picture taken from lunar orbit of the Earth rising above the lunar horizon. Now, this is a very historic photograph. Anybody want to hazard a guess as to what this photograph is?
We are celebrating Ella's graduation.
Okay, yes. This is the Apollo 8 Earthrise photograph. This is the first photograph of an Earthrise ever taken by a human being. This was given on Christmas Eve of 1968, 56 years ago, almost. I think somebody's not muted.
Yeah.
I want to tell them to mute. Okay, anyway, let's go on to the next one. Okay, this photograph was taken about a minute after the first one. Does anybody know what's significant about this photograph? This is the first color photograph of a moonrise taken from the moon. I'm sorry, this is an Earthrise photograph. Both those photographs were taken by the same person. He was one of the first of the first three men to orbit the moon from the Earth. They were on the Apollo 8 mission back in December of 1968. His name was Bill Anders. Go to the next chart. Bill Anders was on the cover of Time magazine at the end of December of 1968 because of the fact that they had saved that year. 1968 was probably one of the worst years in the 20th century that the United States ever underwent because of riots, assassinations, and all kinds of political upheaval. What they did was they saved 1968 and made it on the cover of Time magazine. Unfortunately, Bill Anders died just about a week or so ago. He was 90 years old and he died while he was flying his plane. He was doing a barrel roll. 90 years old, doing a barrel roll, doing what he liked the best. The problem is that I saw on Facebook, and I don't know if this is true, but there was a comment saying that there were major newspapers throughout the United States that didn't think that it was important enough to give his obituary in the newspaper. And I thought that'd be nice for the PVAA at least to acknowledge the fact that we had a true hero. He was a major general in the United States, and he took the first pictures of Earthrise. When he got back from his flight, he said it was very ironic that they had gone to the moon only to discover the Earth. So I just want to pay tribute to my good buddy here, Bill Anders. Okay, next chart. So this is my update to the DART mission. I've given two presentations on this before, but what's neat about this mission is that this is an ongoing process. DART was a spacecraft that was designed and built and actually performed the first impact on an asteroid from Earth. And it's a very neat program. And as you'll find out later on, this is going to go on for several more years. Go ahead. Okay, just a few comments with respect to meteoroids and meteorites. Believe it or not, over 100 billion meteoroids, micrometeoroids, and other space debris with masses larger than 1 microgram enter the atmosphere every day. That's not every year, it's every day. 10 to 50 of those are larger than 10 grams and reach the surface each day. They become meteorites. That whole material that falls onto the Earth's surface amounts to about 48.5 tons of material every day. Now, you might wonder, if that's the case, shouldn't I be concerned about walking around it without a meteoroid umbrella during the day? Well, we got something that is saving us, obviously. And you can see it in this picture right here. This is a picture taken from Earth orbit of the Earth. And what's depicted in this picture is the fact that Earth has two oceans. It has a water ocean, it has an atmospheric ocean. It's the atmosphere, which is the thin blue line that separates the Earth from outer space, that is protecting us. And because of that, we don't have to be worried about getting hit by a meteor or meteorite as we walk around during the day. Okay, Gary.
Yeah, go ahead.
Okay, the problem is that protection only is good up to a certain point. What this depicts is it shows the location of all known bolides, which are meteoroids that come into the Earth's atmosphere that are of any size, that have hit between 1994 and 2013. There's 556 of those objects that are shown there. And as you can see, these objects, which are mostly asteroid material, do not discriminate between the northern hemisphere, the southern hemisphere, the eastern hemisphere, or the western hemisphere. They're pretty much evenly distributed. And if you look at near the top on the right-hand side, you'll see an arrow showing Chelyabinsk. Chelyabinsk was hit, well, actually there was a meteoroid that came into the Earth's atmosphere and exploded near Chelyabinsk back in 2022, I think it was. And, no, I'm sorry. Yeah, I guess it was 2000. Oh, wait a minute, no, that's 2013, I think. Yeah, that was the reason for this being, this map being made, was because of that event. Chelyabinsk was the largest object that entered the Earth's atmosphere and hit the Earth, at least meteorites actually hit since the Tunguska event back in 1908. But what I show on there, look, go back one, just, okay. I'm sorry, just
yeah.
What I want to show here is we have a scale on the bottom that shows the energy of the impacts. And what I have done is I have superimposed on there the energy of the Hiroshima bomb back in 1945 and the Chelyabinsk event that happened back in 2013. What a lot of people don't understand is the material like Chelyabinsk, the meteoroid that hit the Earth's atmosphere of that size, was far larger than the energy produced by the Hiroshima bomb, little boy. Most people don't know that the Hiroshima bomb was very, very small. By today's standard, it really doesn't even show up. Only 1% to 2% of the uranium-235 in little boy actually detonated. All the rest of the uranium-235 was just blown out in the explosion. So it was a very small bomb. It only was about 15 kilotons of TNT. Chelyabinsk was right around about, I think it was 440 kilotons of TNT, which is what they estimated to have been. So Chelyabinsk event was something like about 30 times stronger than the Hiroshima bomb. And what saved us was the Earth's atmosphere.
Okay.
Okay, this is another one to hit this point a little bit harder. I have five different sizes of asteroids on here, going from 4 meters on the left-hand column all the way to 10 kilometers in diameter on the right-hand side. And at the very bottom, I have an estimate for the mass of those asteroids along with the impact energy. And along with those asteroids, I have 5 different explosions that we're familiar with to give an indication of, get a feeling for how big of, how much energy was actually produced in each one of those, would be produced by each one of those objects hitting the Earth. So they're labeled 1, 2, 3, 4, and 5. Number 1 is the Hiroshima bomb, 15 kilotons of TNT. Number 2 is the Chelyabinsk event, about 440 kilotons. The next one, number 3, is the object that formed the Barringer crater, also known as the meteor crater in Arizona. That was about 10 megatons of TNT energy. Number 4 is Dimorphos, which is the asteroid that was hit by the DART spacecraft. That's about 151 meters in diameter. And that energy of impact there was something on the order of, I guess, about 300 megatons of TNT. And then the final one, which is a big one over here for the 10 kilometer asteroid, that is about the same size as the asteroid that hit the Yucatan Peninsula and wiped out the dinosaurs. So that was a big event. Okay. Now, I'll just run through this one really quick. This is a listing of all known meteors, or I should say meteors, but asteroids that have come close to the Earth within 1 million kilometers. This is the complete list. If you look down there about 60% down the list, you'll see that represents the average distance to the moon, about 250,000 miles. There's one event in there that I've singled out. It was an object about 300 meters in diameter. It went by the Earth back in March the 22nd of 1989. And that asteroid was the Asclepius asteroid. What's interesting about that one is that even though that was a fairly good sized asteroid, 300 meters in diameter, nobody knew about it until March the 31st, 9 days later after it had missed the Earth. And it was that event that woke up NASA and the astronomers around the world that they said, we need to do something to get, more telescopes in the sky to, get more information about the orbits of the asteroids. So that was the event. Yeah. And it turns out that every year, March the 22nd is called Near Miss Day. Okay, so like I say, the Earth's atmosphere can help us out and prevent a lot of these things from hitting. The problem is the limit for the atmosphere is somewhere between about 25 meters in diameter and 50 meters in diameter. And that begs the question, what can we do about those? Well, what we can do about those is what's shown on here. These are the different methods that have been thought up for protecting the Earth from large-sized asteroids. On the left-hand side are the nuclear options. On the right-hand side are the non-nuclear options. I won't go through them, but at the very bottom, you'll see there's one that's highlighted in yellow, and that's called kinetic impactor. And that's what the DART spacecraft was all about. Okay, Gary. Okay, now what's interesting about these is the following. The first thing is that the impact of a near-Earth object is the only natural disaster that can be prevented. That's something to think about. That's a very strong statement. And that's why we now have in place, NASA has the task of discovering up to 90% of all the near-Earth objects to make sure that we're protected. No single approach, however, is viable to protect us in all events. So what the studies have shown is that we need probably at least 4 types of mitigation to adequately cover us. The kinetic impactors are adequate to prevent impacts on Earth by moderate-sized near-Earth objects with decades of advance warning. Keep that in mind. Decades. We're talking about at least a decade in advance, be able to get up there in time and deflect an asteroid enough to have it make sure it misses the Earth. So there are 2 things that are very important when it comes to the impactors. Number 1, you need to have very early detection. Number 2, you have to have very precise orbit propagation, or, to propagate the orbit for at least, 20 to 100 years. And you have to do that very precisely. And JPL has probably the most precise solar system ephemerides in existence. And they do an outstanding job on that. Okay. This is a chart I had found on the internet. I modified this a little bit, but it shows a depiction of where these 4 types of mitigation are applicable. We have the nuclear option in the top for the big objects and also for short warning times. We have in the middle the kinetic impactors for the middle-sized objects in like 10, 20, maybe 50 years advance notice. Then on the right-hand side are the tractors. These are gravitational attractions by spacecraft that go up there and go to the one side of an asteroid, and just by their gravitational pull will deflect their course enough, hopefully, to deflect them from hitting the Earth. And the very last one down there on the bottom, which is applicable to all scenarios of civil defense, where you take a whole entire population maybe and take them to the hills. Okay, so here's a rundown on the DART mission. Like I say, it was NASA's first full-scale planetary defense mission to test a method of deflecting an asteroid to protect the Earth. The purpose was to demonstrate planetary defense technology, assess effectiveness of asteroid deflection by a kinetic impactor, and obtain accurate measurements of momentum transferred to an asteroid by an
Gary just disappeared.